In this problem, we see that we have a toroid. So toroid means sort of like a donut shape object, but we have to remember we have to know what the cross-sectional area or what the cross section looks like in a toroid, because some toroids have a circular cross section or an oval cross section. This one has a rectangular cross section, and it could even have a square cross section. So what I mean by the cross section is if we were to take this toroid and we were to make a slice in it, let me try to do that slice kind of 3D here, is that the slice would look like this. And that's the cross-sectional area we're going to have to use in the problem. So this is a rectangular cross-section toroidal shape. This is a toroid, and this is rectangular. Oops, rectangular cross-section, or I like to say pi for plane, and that's just my sort of shorthand for saying cross-section. In this question, it's asking how much flux. So flux is our question mark. Find the flux. Is established in the magnetic path of this figure if the reluctance of the material is given. So given reluctance is equal to 2.80 times 10 to the 5. His reluctance are pretty big numbers. Oops, amp turns per Weber. And we don't have to keep the T for turns. It's not an official SI unit, but it is nice to use, especially in this problem. And I want to find the flux, and it looks like that's all we have in this question, but we do have more information, and it is drawn on the diagram. We have 500 turns here. 500 turns, so N equals 500. And I'm going to keep this unit because, of course, we wouldn't usually keep turns as a unit, but I'm going to say T because that's going to help my math. And then it looks like I have current as well, I. And whenever I see that I have current, then a current and number of turns, I immediately remember one of my formulas that has FM in it. And this is what happens to me when I see current and number of turns. I remember I have a formula that says my magnetomotive force actually is equal to the number of turns times the current going through it. So that's just prompted in my brain. Not sure if I'm going to need that yet, because I have to find flux. Now let's think about my formulas that have flux in it. So find flux. Well, if I think about my formulas with flux in it, the most basic formula, I don't really care about flux density right now, but my basic formula is reluctance is equal to magnetomotive force that causes the flux over the flux. And this is basically Ohm's law for a circuit. It says the FM that is established over here, the FM that is given over here, basically made over here, establishes these lines of flux that are going to be going through this material. And of course, they have to be a continuous path. And there's going to be lines of flux on the outer circumference. There's going to be lines of flux on the inner circumference, and there's going to be lines of flux in the middle as well. I'm not going to put the arrows on because I haven't given any thought to the right-hand rule for the direction of the flux in this case. And I don't think I really need it. So that's my, it's like my Ohm's law, right? For electric circuits, but it works for magnetic circuits in sort of the same way where my flux that I want to find is kind of like current, right? So I'm going to rearrange this formula, and I'm going to say my magnetic flux lines are then just going to be equal to Fm over Rm it's a function of the amount of magnetomotive force that this circuit has divided by how reluctant this circuit is in order to establish that magnetic flux. And we remember, of course, that Fm is the sum of the number of turns times the current that's going through it. That's what's driving this flux to be developed. So there were 500 terms. If there's more turns, then of course you'd be driving the establishment of more flux lines, right? If there were more current than 0.3 amps, then you would be establishing more flux and then dividing that through. It is that reluctance that is reluctant to make that get established into flux. And if this number is really high, then you're going to have less flux. If this number is low, then it says, you know what? I'm not very reluctant. You can go ahead and establish a lot of flux. So this was just given in the question. These were just given in the question. And really this whole problem just boils down to putting the values into your formula. I'd like you to remember the significant digits and remember if there are 3 significant digits in the problem, which I'm going to pretend there are. Here we go. If there's 3 significant digits in the problem, then let's answer it also in 3 significant digits. This textbook answer is using 3 significant digits. There were actually 2 in the problem, but I rewrote the problem here to have 3 significant digits. And once I look at my units here, let's make sure that we all understand what units are looking like. This amp is going to get crossed out with this amp. I've carried along the word turn, so that crosses out with this turn. I have 1 over Weber in the denominator, which of course mathematically just means Weber is in the numerator. Let's take a look at, now we look at this textbook answer. We said this is 300, it's 536 microweber. So let's see what I have. I said 5.36 times 10 to the negative 4. So let's move this decimal place 4 times this way then. And if I do that, so I'm going to do 5.36, and I'm going to move the decimal place 4 times. 1, 2, 3, 4. So now the decimal place is here. So 0, 0, 0, right? There we go. And that is 5.36 times 10 to the negative 4. Okay. And then, but the question is saying, well, it's 536 microweber. Well, I like that. I think they've been pretty smart with that, because what they've done is they have then taken that decimal place and they've gone 1, 2, 3, 4, 5, 6. And that now they've got it here. So 536 microweber. Micro meaning six decimal places. So remember, micro means 6 decimal places. Well, micro doesn't mean 6 decimal places, but micro anything, to get to micro anything, you would move 6 decimal places, because that's what it is relative to 1. So that's how you get from 5.36 times 10 to the negative 4 to 536. I would put a decimal place there just to be clear that we have 3 significant digits and the units of microwebers. Of course, we can't just call this 356 webers. We call it microwebers. And I just remind you that Weber is such a big unit. We usually use micro because Webers are huge. Webers are huge. So we are often expressing our answers in microwebers. So this is a nice example to illustrate that.